In this video, we're going to learn how to do related rates problems. So for our first problem, suppose that an object is moving along the curve y equals x squared with dx dt at x equals 3 equal to 4, and we want to find dy dt at x equals 3. So physically what this means is dx dt is the rate of change of the x-coordinate with respect to time, so it's kind of like the velocity in the x direction. And then dy dt is kind of like the velocity in the y direction. So we're given the path y equals x squared, we know the velocity in the x direction at a particular moment in time, and we want to find the velocity in the y direction at that same moment in time. Now the way we do this is we take that derivative, dy dt, and we break it up into the product of two derivatives that we actually know. The way we break it up is to use the chain rule. The chain rule essentially just lets us treat a derivative like a fraction. So when we multiply derivatives, we can cancel any terms that appear in both the numerator and denominator. So what we're going to do is we're going to take that derivative, dy dt, and we're going to break it up. So it'll be dy over something, then times something over dt. Now we know that dx dt at x equals 3, that's equal to 4. So that's a very strong indication that one of these terms in the product should be dx dt. So this one over here. And since we're putting x in the numerator, in order for these two terms that are being multiplied together to cancel out to yield dy dt, we have to make this denominator dx as well. That way it's like the dx's cancel out, and all that we have left is dy dt. So let's go ahead and substitute what we know. We'll just leave this as dy dx for now, and then this is times dx dt, which is 4. Okay, so now we want to find dy dx, and we can do that using our curve here. We know that y equals x squared, so we can differentiate both sides, get dy dx is the derivative with respect to x of x squared, which means dy dx is equal to 2x. And of course we're interested in the particular moment when x is equal to 3, so dy dx at x equals 3 is equal to 2 times 3, which is 6. So we'll go ahead and plug that into here. We get that dy dt is equal to 6 times 4, and the result of that, 6 times 4 is 24. So there we go. Dy dt at the moment when x equals 3 is equal to 24. Final answer. Here's the next problem. We're given that r equals cosine of theta, and that dr dt when theta equals pi over 4 is equal to negative 3, and we want to compute d theta dt when theta equals pi over 4. So again, we're going to use the same strategy. Take that d theta dt and break it up into a product of derivatives, each of which is easier to compute, and so that the product is equivalent to our original derivative. So d theta over something times something over dt, where the somethings are the same. So it's like they cancel in the chain rule. Okay, so now we look for any given information about another derivative. Hey, it's right here. We know that dr dt when theta equals pi over 4 is equal to negative 3, so why don't we make this a dr dt? That way we can just plug in for dr dt, and now so that these fractions cancel, we want this denominator here to be the same. So d theta dt is equal to d theta dr times dr dt, and dr dt we know is just negative 3. So now it remains to find d theta dr. And we can go ahead and do that using this equation here that we're given, r equals cosine of theta. Now you'll notice that we're looking for d theta dr, not dr d theta. So if we just differentiate r with respect to theta, that won't be the result that we want to get. We'll be getting dr d theta, but we want d theta dr. But there's a very easy way to remedy that. If we get dr d theta, then we can just flip the fraction, take the reciprocal, and then that'll give us d theta dr. Again, it's kind of like derivatives are just fractions, and we can work with them in the same way that we work with fractions. So let's go ahead and differentiate with respect to theta. So dr d theta equals d over d theta of cosine theta, which means dr d theta is equal to negative sine of theta. So at the moment when theta equals pi over 4, dr d theta at theta equals pi over 4, that's equal to negative sine of pi over 4. And sine of pi over 4 is just root 2 over 2, so negative root 2 over 2. And now since we want to compute d theta dr, all we have to do is take the reciprocal of both sides. So d theta dr at the point when theta equals pi over 4 is equal to the reciprocal, so 2 over square root 2. And we can simplify that, so d theta dr when theta equals pi over 4, that simplifies. 2 over root 2 is just root 2, so negative root 2. D theta dr is negative root 2, and then that times negative 3. 3 root 2. So there we go. There is our result. D theta dt at the moment when theta equals pi over 4 is equal to 3 root 2. So now we've been introduced to the concept of related rates, and in the future we'll continue to get lots of practice working with related rates. In particular, we'll be learning how to apply related rates in geometric scenarios, such as with the dimensions, area, and volume of circles, spheres, squares, and cubes.